Hey everyone, welcome back to Airwise Academy, your trusted source for ESA Part 66 learning. Today, we're concluding the mechanics submodule with a fundamental and fascinating topic, Section 4, Fluid Dynamics. This section is all about understanding the behavior of liquids and gases, knowledge that is absolutely essential for grasping aerodynamics, hydraulic systems, and propulsion. We will break this down into two logical parts. In Part A, we will start by defining the basic properties of fluids, namely specific gravity and density. Then, in Part B, we will build on that foundation. We'll explore more complex concepts like viscosity and fluid resistance, and see how streamlining helps to reduce drag. We'll also investigate the effects of compressibility on fluids, which is critical for high-speed flight. Finally, we will arrive at one of the most important principles in aerodynamics, the relationship between static, dynamic, and total pressure, beautifully described by Bernoulli's theorem and demonstrated by the Venturi effect. For Part A on specific gravity and density, both B1 and B2 trainees need to achieve knowledge level 2. For the topics in Part B, there is a key difference. The concepts of viscosity, fluid resistance, and streamlining require knowledge level 2 for B1 engineers, but only knowledge level 1 for those in B2. The subsequent topics on compressibility and pressures with Bernoulli's theorem are vital for all. All right, let's begin our exploration of fluid dynamics. Moving on to fluid dynamics, we begin with a fundamental property, density. Density is defined as a substance's mass per unit volume. It is calculated simply as mass divided by volume. The units differ between systems, pounds per cubic foot in imperial and grams per cubic centimeter in the metric system. Consider this example. A container with a volume of 24 cubic feet holds a liquid weighing 1,497.6 pounds. Using the formula, its density is calculated to be 62.4 pounds per cubic foot. This is, in fact, the density of water at 4 degrees Celsius, which is used as a standard for comparison. Temperature has a critical effect. While mass remains constant, heating or cooling a substance changes its volume through expansion or contraction, thereby changing its density. For gases, pressure is a major factor. A gas's density increases in direct proportion to the pressure applied to it. Therefore, standard conditions of 0 degrees Celsius and a pressure of 760 millimeters of mercury are used as a baseline for measuring and comparing gas densities. Let's now discuss specific gravity, which is a crucial concept for comparing material densities. Specific gravity is defined as the ratio of the weight or density of a substance to the weight or density of a standard. For liquids and solids, this standard is water. It is calculated using either of these two formulas, which are functionally the same. A key point is that specific gravity is a dimensional quantity. It's a pure number. For instance, a hydraulic fluid with a specific gravity of 0.8 means that 1 cubic foot of it weighs only 80% as much as 1 cubic foot of water, which calculates to 49.92 pounds. To measure specific gravity in practice, we use an instrument called a hydrometer. It consists of a weighted glass float with a graduated scale housed within a sampling tube. The principle is straightforward. The depth to which the float sinks indicates the liquid's density. In a denser liquid, the float is more buoyant and rises higher, showing a greater specific gravity. In a less dense liquid, it sinks lower. A critical application in aviation is checking an aircraft battery. The specific gravity of the battery acid, or electrolyte, tells us its state of charge. A discharged battery shows a reading around 1.150. while a fully charged one will read between 1.275 and 1.310. Now, let's move to the core principles of fluid mechanics. First, a fluid is any substance that flows, including both liquids and gases. A critical distinction between them is compressibility. Liquids are largely incompressible, while gases are highly compressible. Understanding fluid behavior is fundamental to aviation, explaining phenomena from wing lift to hydraulic system operation. The cornerstone of hydraulics is Pascal's law, established in 1653. It states that pressure applied to a confined fluid is transmitted undiminished throughout that fluid. This pressure acts equally in all directions and always at right angles to the walls of its container. It's important to distinguish this from the pressure caused solely by a fluid's weight or hydrostatic pressure. In that case, pressure is equal at any given depth, but it increases the deeper you go. Now, let's examine Pascal's law in action, which is illustrated in this figure. The principle is this: an external force on a piston creates additional pressure in a confined fluid. According to Pascal's law, this applied pressure acts equally and undiminished in all directions, reaching every point in the fluid. Consider this example. With an applied pressure of 100 psi, this value is added to the existing hydrostatic pressure at every depth. So, the bottom gauge shows 100 psi plus the 8.34 psi of hydrostatic pressure, giving a reading of 108.34 psi. Similarly, the middle gauge shows 100 psi plus 4.17 psi for a total of 104.17 psi. This clearly demonstrates how a localized force creates a uniform pressure increase throughout a closed hydraulic system. Now, let's introduce the core mechanical relationship derived from the principles of fluid pressure, the interplay between force, pressure, and area. This relationship is defined by a fundamental formula: force equals pressure multiplied by area. From this single equation, we can derive the others. If you need to calculate pressure, you rearrange it to force divided by area. Similarly, to find the area, the formula becomes force divided by pressure. To help easily recall these relationships, we use a visual aid known as the magic triangle, illustrated here in this figure. It's a simple tool to use. Just cover the variable you want to find, and the positions of the remaining two will show you the calculation. Cover F for force, and you see it's P multiplied by A. Cover P for pressure, and the formula is F divided by A. Cover A for area, and you see it's F divided by P. This triangle provides a quick and reliable way to apply this essential relationship in any situation. Here we have a simple hydraulic system, as shown in the figure. It consists of a single piston where an input force of 5 pounds is applied to a piston area of 0.5 square inches. To find the system pressure, we use the basic formula: pressure equals force divided by area. So, 5 pounds divided by 0.5 square inches gives us a pressure of 10 psi. The key takeaway is Pascal's law. This pressure is transmitted equally in all directions throughout the entire fluid. In other words, every part of the confined fluid experiences the same 10 psi pressure. Now, let's look at a slightly more advanced hydraulic system shown in this figure. Here, the first cylinder is connected to a second cylinder with a much larger piston. The input force of 5 pounds still generates a system pressure of 10 psi, which is transmitted throughout the fluid. On the larger piston, which has an area of 5 square inches, this 10 psi produces an output force calculated as pressure times area. 10 psi multiplied by 5 square inches equals 50 pounds. This illustrates the key advantage of hydraulic systems: mechanical advantage. By dividing the output force by the input force, we find a mechanical advantage of 10. In practical terms, a small 5-pound input can lift a 50-pound load. Let's explore a fundamental principle in hydraulics: the conservation of work. This principle tells us that in an ideal, 100% efficient system, the work you put in is equal to the work you get out. Work is calculated as force multiplied by distance. Therefore, if a hydraulic system increases the output force, it must reduce the output distance. You simply cannot get more work out than you put in. To understand this trade-off, we look at the volume of fluid displaced. The volume moved by a piston is its area multiplied by the distance it travels. For example, a piston with an area of 2 square inches moving 10 inches displaces 20 cubic inches of fluid. This displaced volume links the input and output sides of the system. Now, we come to a core principle of hydraulics: volume displacement. The fundamental rule is that in a confined system, the input volume must equal the output volume. Simply put, the fluid displaced by the input piston must be accepted by the output piston. We express this mathematically as input area multiplied by input distance equals output area multiplied by output distance. This relationship is practically demonstrated in the figure. Here, you can see a small input piston moving a large distance of 20 inches, which forces a large output piston to move a much smaller distance of just 1 inch. This visual example perfectly confirms the fundamental trade-off between force and distance in hydraulic systems. Let's go through a complete practical example using the same setup as shown in the figure from the previous slide. Here, a 50-pound input force is applied to a small piston with an area of 0.25 square inches, generating a system pressure of 200 psi. This pressure is transmitted to a much larger output piston of 15 square inches, producing an output force of 3,000 pounds. The mechanical advantage, the ratio of output force to input force, is therefore 60. Next, we consider the movement of the pistons. The input piston moves 30 inches, giving a displaced fluid volume of 0.25 times 30, which is 7.5 cubic inches. This volume must be received by the output piston. Dividing 7.5 cubic inches by the output piston's area of 15 square inches, we find the output piston moves only 0.5 inches. This clearly demonstrates the force-distance trade-off in hydraulic systems. A large gain in force comes with a proportional reduction in movement. Now, let's move beyond pure formulas to a conceptual analysis of hydraulic systems. While the formulas are essential, recognizing the underlying relationships is the key to true understanding. The system's performance is fundamentally determined by one thing: the area ratio. We can express this with two powerful relationships. The output force is approximately the input force multiplied by the area ratio, output area over input area. Conversely, the output distance is approximately the input distance multiplied by the inverse of that ratio, input area over output area. Let's apply this to a quick analysis from the figure. With an input piston area of 0.25 square inches and an output piston area of 5 square inches, the area ratio is 20. This single number allows us to conclude without complex math. The output force is 20 times the input force. The output distance is only 1/20th of the input distance. Therefore, the system provides a mechanical advantage of 20. This demonstrates how a simple ratio reveals the entire story of force multiplication and distance trade-off. Let's explore Bernoulli's principle, a fundamental concept governing fluid behavior. The principle itself is this: in a flowing fluid, an increase in velocity results in a decrease in static pressure, and vice versa. This holds true provided no energy is added to or lost from the system. The Venturi tube shown in the figure is the classic demonstration of this principle. It is a tube with a constriction, forming a converging and then a diverging duct. To understand why this happens, we must consider the energy types within the fluid. Static pressure represents the fluid's potential energy. Velocity represents its kinetic energy. These are related through the total pressure relationship. Total pressure equals static pressure plus dynamic pressure. In an ideal, lossless flow, this total pressure remains constant. Therefore, when the fluid accelerates through the constriction of the Venturi tube, its kinetic energy, velocity, increases, forcing a corresponding decrease in its potential energy, the static pressure. Let's apply this to the Venturi tube. In the wide sections at points A and C, the fluid moves slowly, resulting in high static pressure. As the tube narrows, the same volume of fluid must pass through a smaller area, so its velocity must increase in the constriction at point B. According to Bernoulli, this increase in velocity causes a drop in static pressure. A classic application of this is in a float-type carburetor. Air entering the engine is forced through a venturi. The resulting low static pressure in the venturi draws fuel from the carburetor's bowl, creating the essential air-fuel mixture for the engine. Now, let's apply Bernoulli's principle to understand how a wing generates lift. The key lies in the wing shape. The curved upper surface acts like the top half of a venturi tube. Here is the process. Air flowing over this curved top surface is constricted and forced to accelerate. According to Bernoulli's principle, this increased velocity causes a decrease in static pressure on top of the wing. Meanwhile, the air moving along the flatter bottom surface experiences less acceleration, resulting in a higher static pressure. The resulting pressure difference between the upper and lower surfaces creates an upward force. This is lift. It is important to note that this topic is foundational. The principles of aerodynamic lift will be explored in much greater depth in Module 8, Basic Aerodynamics. Let's now define a fundamental fluid property: viscosity. Viscosity is the internal resistance of a fluid to flow. We can understand this through common examples. A fluid with low viscosity, like gasoline, flows very easily. A fluid with high viscosity, like tar, flows very slowly. A key factor affecting viscosity is temperature. For most fluids, viscosity increases as temperature decreases, making them thicker and more resistant to flow. Understanding viscosity is critical in aviation for several key systems. In hydraulics, fluid must be viscous enough to create seals between parts, but not so viscous that it resists flow and causes power loss. In aerodynamics, viscosity determines the characteristics of the boundary layer and affects how air flows over aircraft surfaces, influencing both lift and drag. In lubrication, the correct viscosity is essential for creating a protective film between moving parts to prevent wear and manage heat. Now, let's discuss how we quantify and measure viscosity, focusing on the viscosity index and the viscometer. First, the viscosity index, or VI, is a dimensionless number that indicates how much a fluid's viscosity changes with temperature. A low VI signifies a large change in viscosity with temperature. This is considered poor performance, as the fluid's properties are unstable over an operating range. A high VI signifies a small change in viscosity. This stable performance is highly desirable for consistent operation in varying climates. To obtain this index, we must first measure viscosity. A standard instrument for this is the Seybold viscometer, illustrated in this figure. Its operation is straightforward. It measures the time in seconds for a fixed volume of 60 milliliters of fluid to flow through a standardized orifice at a controlled temperature of 100 degrees Fahrenheit. The result is the viscosity expressed in Seybold universal seconds, or SUS. And finally, we come to the practical application of these fluid principles: streamlining. Streamlining is the deliberate, gradual shaping of an object, like a wing or a pipe bend, to allow fluid to flow around it smoothly, without tumbling into turbulence. This is critical for two main reasons. In aerodynamics, it is essential for the smooth airflow that creates lift. In aircraft systems, it reduces resistance and heat buildup in fluids moving through pipes. In summary, streamlining is the key to minimizing drag and maximizing efficiency in any interaction between a fluid and a solid object. And that brings us to the end of this submodule, and our journey in mechanics has come to an end. Now, let's warm up with a few questions to review what we've learned. Now, let's get started with question 1. Under standard conditions, what is the relationship between the pressure exerted on a gas and its density? A. Density decreases as pressure increases. B. Density increases in direct proportion to pressure. C. Density is unaffected by changes in pressure. The correct answer is B. Density increases in direct proportion to pressure. As we mentioned earlier, pressure is a critical factor for gases. When more pressure is applied to a gas, its molecules are forced closer together. This decreases the volume the gas occupies. Since density is mass per unit volume and the mass of the gas remains constant, this decrease in volume results in a direct increase in density. This is different from liquids and solids, where density is less affected by pressure. The standard conditions mentioned are 0 degrees Celsius and a pressure of 760 millimeters of mercury. Question 2. A hydrometer reading for an aircraft battery's electrolyte shows a value of 1.300. What does this indicate? A. The battery is fully charged. B. The battery is discharged. C. The specific gravity of the electrolyte is less than that of water. The correct answer is A. The battery is fully charged. If you remember, the specific gravity of the electrolyte in a charged aircraft battery is between 1.275 and 1.310. A reading of 1.300 falls squarely within this range, indicating a charged state. When a battery discharges, the specific gravity of the electrolyte decreases. A reading of approximately 1.150 indicates a discharged battery. Furthermore, since the specific gravity of water is 1.00, any value above 1 means the substance is denser than water, making option C incorrect. Question 3. According to Pascal's law, how does pressure transmitted by a fluid act on the walls of its container? A. It decreases with depth. B. It acts equally in all directions at a given level. C. It is only felt at the bottom of the container. The correct answer is B. It acts equally in all directions at a given level. Pascal's law states that pressure set up in a confined fluid acts equally in all directions and at right angles to the container's surfaces. This fundamental principle means that pressure applied to an enclosed fluid is transmitted undiminished to every portion of the fluid and the walls of the container. While the pressure increases with depth due to the fluid's weight, the additional pressure from an external force is distributed equally at any specific height. Question 4. If a force of 500 pounds is applied to a piston with a surface area of 10 square inches, what is the resulting pressure in the fluid? A. 50 psi, B. 500 psi, C. 5,000 psi. The correct answer is A. 50 psi. This is calculated using the fundamental formula from Pascal's law. Pressure equals force divided by area. So we take the force of 500 pounds and divide it by the area of 10 square inches. 500 divided by 10 gives us a pressure of 50 pounds per square inch, or 50 psi. This calculated pressure would then be transmitted equally throughout the entire confined fluid system, demonstrating the practical application of Pascal's law in hydraulic systems. Question 5. In a hydraulic system, an input force of 10 pounds is applied to a piston with an area of 0.5 inches square. This is connected to an output piston with an area of 5 inches. What is the mechanical advantage of this system? A. 5, B. 50, C. 10. The correct answer is C. 10. Let's see why. First, we use Pascal's law to find the system pressure. Pressure is force divided by area. So 10 pounds divided by 0.5 square inches gives us 20 psi. This pressure is transmitted equally throughout the fluid. Next, we calculate the output force. Force is pressure times area. So 20 psi multiplied by the output area of 5 square inches gives an output force of 100 pounds. Finally, mechanical advantage is the output force divided by the input force. 100 pounds divided by 10 pounds equals a mechanical advantage of 10. This means the system multiplies the input force tenfold. Question 6. In a hydraulic system, if the input piston has an area of 2 inches squared and moves 10 inches, and the output piston has an area of 10 square inches, how far will the output piston move? A. 2 inches, B. 5 inches, C. 50 inches. The question involves calculating the distance an output piston move in a hydraulic system. We use the principle that the volume of fluid displaced by the input piston must equal the volume received by the output piston. The formula is input piston area times distance moved equals output piston area times distance moved. Plugging in the values, 2 square inches times 10 inches equals 10 square inches times the unknown output distance. This gives us 20 cubic inches. To solve for the output distance, we divide 20 cubic inches by the output piston area of 10 square inches, resulting in a movement of 2 inches for the output piston. This demonstrates the trade-off between force and distance in hydraulic systems. Question 7. A hydraulic system has an input piston area of 0.5 inch squared and an output piston area of 10 inch squared. If an input force of 20 pounds is applied, what is the mechanical advantage? A. 10, B. 20, C. 40. The correct answer is B. 20. While mechanical advantage can be calculated as output force divided by input force, we can determine it more directly by comparing the areas of the pistons. The mechanical advantage equals the output piston area divided by the input piston area. Here, 10 square inches divided by 0.5 square inches gives us a mechanical advantage of 20. This means the system will multiply the input force 20 times, so the 20-pound input force would generate a 400-pound output force. Question 8. According to Bernoulli's principle, what happens to the static pressure of a fluid when it flows through a constricted section of a Venturi tube? A. Static pressure and velocity both increase. B. Static pressure increases while velocity decreases. C. Static pressure decreases while velocity increases. The correct answer is C. Static pressure decreases while velocity increases. Bernoulli's principle states that for an incompressible fluid with no energy added or removed, the total energy remains constant. This total energy is a sum of the static pressure, potential energy, and the dynamic pressure, which is related to velocity, kinetic energy. As the fluid enters the narrow section of the Venturi, it must accelerate to maintain the same flow rate, meaning its velocity increases. To keep the total pressure constant, this increase in dynamic pressure, velocity, must be accompanied by a decrease in static pressure. This inverse relationship is the core of Bernoulli's principle and is fundamental to explaining how aircraft wings generate lift. That's all for today's lesson. If you found this video helpful, please give it a thumbs up and consider subscribing to Airwise Academy for more aviation knowledge. We'd love to hear your thoughts or questions in the comments below. Turn on notifications so you won't miss our upcoming videos. Until next time, blue skies and happy learning!